we can move to the last session of today, that is about FAIR data. I kindly ask Irini to come on stage for the presentation.
No, spoil.
Sorry, just try.
Yes, it was a little dragon. I would like to dedicate this presentation to a new friend I made here in the nanosafety school, to Cynthia, because she's going actually in the FAIR hero's journey, which is actually fighting dragons more than FAIR data. Because behind every data set, there is a beast. And in order to destroy and to fight those dragons, we know first to know thy enemy. So we were going to see through the journey of SSbD what type of enemies we can see and how to defeat them. First, the prophecy. In 2016, an ancient rune was written with 4 commands. Ye data shall be fair, findable, accessible, interoperable, and reusable. Why fair? Because for digitization to happen and to take knowledge into data and data into decisions, we need the data to be fair to accelerate this process. But it's much easier to write down visions than to actually make the data fair. Or, as Louis C.K. said once, I believe in all the 15 sub-principles of the 4 FAIR pillars, but I live by none of them. So the SSbD starts with the scoping phase, as you can see in the table of ideation. And we did this exercise actually yesterday, where we created 3 teams across case studies. Why? Because SSbD, a pre-market approach, is highly multidisciplinary, and there need experts across all the life cycle stages. So they sit down, they discuss about the case study, and they discuss about material processes and products across the life cycle stages. And what lurks behind each stage is FAIR dragons. Then, the more deep you look into the life cycle stages, you realize that more dimensions of FAIR issues exist, because you have environmental aspects, you have safety, human safety aspects, you have functionality aspects, and of course you have cost, and as we saw, you also have social aspects on top of all of these. Then the project starts, and all the partners, they start creating data sets. It can be functionality, safety, environmental, but there can be experimental data, they can be simulated data, it can be modeled data, it can be literature, it can be deliverables. So data actually have many forms, as we will see. In the synthesis stage, I call this dragon the metadata eater. Why? Because a lot of papers, they will discuss about how they synthesize this new innovative material, but sometimes you won't find exactly the metadata you need in order to make the synthesis reproducible. So, you know, the process should be described, the step-by-step synthesis, the reagent, the CAS numbers, the concentration, the duration of each step, if you applied any external energy to the system. And something that is missing a lot of the times is also the yield of the reaction, and also the scale of that synthesis process. So all these have to be documented. And if you don't gather this data, we're just feeding the metadata dragon. And we also do the characterization, because how can you trust what a nanomaterial does if you don't know how it was made? And here, when it comes to the peak properties, each measurement needs to have context. For example, zeta potential 20 millivolt. Okay, but where? Measured in this medium, measured with this instrument, at this pH level, right context. So we can just add information in everything we do, the replicas, the standard deviations, you name it. But you will see that we have, as a community, guidelines. Like, for example, this is the OECD. This is the OECD just for one agglomeration. This is just for agglomeration. 42 pages of how to report the agglomeration in the best way possible, but we are not going to lose completely our hair. That's why we have the minimum amount of information, where we say, okay, what is the minimum amount of data I have to capture, but also root it in quality. So they do exist, some metadata out there. So before you do your experiments, perhaps we should check if some metadata with minimum amount exists. But in any case, those big documents of OECD guidelines, in the end, they tell you report everything before, during the nanomaterial, and also after, and storing conditions. So this is to encapsulate. But there are already templates to help us report the physicochemical properties. And if you don't like those, eNanoMapper is actually building a template wizard. They call it a template wizard, where you can go with a data provider and co-create your own template. For chemicals, the machine-readable ID, like cast numbers, is old news. When it comes to nanomaterials, this doesn't exist, but I found two very notable examples. The European Registry of Materials, which it gives you global persistent identifiers to not get lost in translation when you talk about your nanomaterials, because you can have one silver nanomaterials, but 10 silver nanoforms. Then we have the nanoINCI. This is for the very courageous fighters, because it's a codified, three-layered codification system of your nanoform in order to describe from the core to the surface ligands. All this in a codified manner. And this could actually be used for each legislation in order for you to describe the nanoform. It's a potential candidate for the future. For repositories, there are many, and depending on what you study, if you are in the health science, people like to put the data in open science framework, or if you are into modeling, people use GitHub. So depending on the field of your research, there are different repositories available. But what I want to mention here is by just putting the data somewhere, you actually tick almost half of the FAIR principles by making them accessible, findable, and interoperable. Now, when it comes to ontologies, which is I would say, a very difficult dragon to defeat, the ontos dragon, because there are many, right? You have different ontologies for the material, different ontologies for the experiment, different ontologies for toxicological information, but usually you use a combination or lookup services or the BioNano portal, but they are so slow. That's why in eNanoMapper, I found this actually 2 weeks ago. They have this annotator where you just put the text you want and it annotates it very fast. It gives you all of the information you need. So this is brilliant in my opinion. When we go in the life cycle stage 2, which is the manufacturing stage, things become a little bit more difficult because we're entering the realm of digital twins, Industry 4.0, Industrial Internet of Things, digitization of all those buzzwords. But in reality, the goal in the end is simple. Let's document the process as good as we can because it really matters. So we can start by describing the process itself, if it's a continuous, what stages does it have, even put graphs to help to help the data put into a context. You know, when you can put all the process parameters that are for this machinery. I mean, of course, because we are into the manufacturing stage in SSbD, we might also have occupational exposure measurements because we care about the occupational safety. And here you have to reply the aerosol measurements, the location that you did the measurements, the type of instruments, the sensors, because this is very important, the metrics, the units. And I'm not even touching about release and emissions because I'm afraid I will encounter the LCA dragon and I will leave that for the next speaker. Now, we actually tried to do this in a project where we created a template, me and the 6 people that they were doing the exposure measurements, because the time series raw measurements of the exposure campaigns, I wasn't able to quite understand I didn't like them for someone who is not an expert in occupational settings. So I wanted something simple, so that's what we did. So in this template, for example, you can see the institution, who did the measurements. You can see the creators, who were the people who did the measurements. Here we have descriptors, we have images, we describe the process, if it's automated. We have the different information of the sensors, the instruments, near field, far field, before the process, during the process, after the process, offline, gravimetric. Then I cleaned a little bit the data that they were given from the 6 different partners. We put down all the protocols, all the instruments that were used, and finally this is a descriptors tab that it's AI ready, right? It's harmonized. And of course, some ontologies term. But there are other templates. There is also a gracious template to capture occupational exposure measurements. And of course, there are 65 different manufacturing ontologies. And this is a Hydra dragon, as you can see, because when you go in the manufacturing, you have the raw material, you have classes, you have subclasses, and the ontology have layers, and it's quite complicated. From the 65 manufacturing ontologies, a recent review said that only 20 actually work. So this is meno male. Then we also have exposure ontology for the occupational, which later was also extended. So this is nice to have. And of course, it was extended to also capture the product. I don't like the product because it's a dragon where you don't know where to capture, where to press, you don't know where to begin. The product could start from the life cycle stage 1 of the design, could be the manufacturing, maybe it's the distribution, or maybe it's the use phase. What about the maintenance? Is your product even physical? Could be a service. And what happens in the end of life? Is it still there? Is it break down? Or is it gone? Is it reused? So there is a massive challenge to make the data fair, to put actually in a context for people can reuse it, to link all the life cycle stages. And what happens in the research when there is a massive challenge? More people come. So we have a new hero, the Digital Product Passport, which is actually an initiative of the eco-design for sustainable products, where they want actually to document the data. How is the product, where did the product came from? How is it made? The environmental footprint, its circularity. And the European project, DigiPass, they actually want to give us a tool, an ultimate weapon, where they want to make a platform, not just for product passport, but for materials and product passport. So this is going to be very exciting coming years. Now, as you can see, the fair, it's not just one person to capture, to make it interoperable, to make it the ontologies. So we need a team. And the most important part is the people who make the data. Like, when someone is asking you data, don't be the dragon yourself, share the data. So we need data annotators, curators, so it's a big party, or a data shepherd that provides everything in 0.5% of the price. Enough with fighting, let's see what a tiny medieval victory looks like. First, you start from the grant agreement and you learn it by heart, because it gives you a lot of information. You actually understand what type of data are going to be generated and from which partner. It has information of the protocols, of the standards, right? So you can have already, before the project even starts, by the moment of acceptance, you can already imagine the type of data that are going to come. But because I hate 40 pages, to read 40 pages every time, I suggest for each case study to make a snapshot. Try to capture each case study in one page, put it on the wall, leave it there, just so you know the type of data and from whom and how they are linked. Then you have to involve each person who is doing the measurements or the modeling and talk with them, go through the templates and refine these templates. And this is what I did for 4 years in a project called Asina, where I gathered all the information that was being generated in this SSbD case study for 2 case studies. And this is a paper under review where I tried to make the data not just fair, but open. So people could see what it means to be fair as possible. So what I did is to gather the institution, the data creators, who are they, what did they measure, a little bit a cleaner version of the data, the protocols they use, the instrument they use, and the AI-ready file. The AI-ready file was inspired from this paper that they said a different type of FAIR acronym. They said findable and AI-ready. And that's what that tab descriptor is about. And don't worry if the data you give are in Excel sheets, because the spreadsheets can be fair. With a sparser, we can transform into machine readable, so don't worry. Just very quickly to show you the data. So you have life cycle 1, life cycle 2, life cycle 3, life cycle 4. The dimensions inside. Let's see life cycle 3. Safety, functionality, environment. Life cycle 1, you go into safety elements. Human, lung, intestine, in vitro. Let's see the lung. So you have the people, the institution where those data came from. You have the creators that measure the data. You have the raw measurements, the way they came. Then you document the protocol, what they did with the dispersion, sonication, and the toxicological endpoints. Then you have the instruments they use, and of course the descriptors, which is AI ready, and it's my favorite because it's my background. And of course ontology and descriptors. So we did this for all the 22 data sets for 1 case study. And but the time flies, and it's not medieval times anymore. There are many tools available. Instance map, for example, there he is. Sitting there, Poons, which is a very nice way to visualize all this template into 1 image and to link protocols and materials. The template wizard is coming. We have tools online to increase the metadata for our measurements. And in any case, what I want to say that while the tools are very important, it's actually a community effort. It's the consortium communicating with each other and being open to share the data. Perfect fairness does not exist, but it's very aspirational, something to strive for, and that we should start from day 1, because it's during the project, before the project even, and after. So there is plenty of room of improvement on the way we capture data from projects. And thank you very much.
Thank you very much, Irini, for this impressive presentation. So then we can take the questions at the end, and we can move to the next presentation. The speaker is already here. It's Jonas. You already know. It's about FAIR data applied in LCA, right?
Correct, yeah. Hi, it's me again, Jonas Hoffman from GreenDelta, talking now a bit about FAIR principles in the LCA world. I think we have a nice introduction already into FAIR principles in general. Perfect. Yeah. I forgot to tell before, earlier this morning, I'm also representing the SiToLub team, which is also here. So kudos to them. Talking about LCA, so it's a bit more applied because it's already a very established industry and a lot of softwares are used. Shortly to us, very shortly why we're here and what we're doing basically. So our company is working with a lot of data. So we have the issues with the FAIR data a lot. We provide an open source software, and that's why we're very committed to use also FAIR principles for data sets in general. So it's a training school, a bit more about LCA and how we do it at the end of the day. So normally you have databases, you have a software, you have data formats. Everyone uses something different. If you want, you can stick to Excel. It's fine, you can do it. It's not very modern, and also it works quite good for part card footprinting. If it comes to more complex situations, like in LCA, for sure you will stick to a software. There were a lot, some are also represented here at the conference, so you can choose software, and also then you can use a respective database, depending what you do. We saw it for social LCA, But of course, you can also do it for LCA in general. There is a plethora of databases present. You choose the one you're most interested to, depending on the sector you're working in. And sometimes they're also complementary to each other. So it depends a bit what you're opting for, but normally this is what you do. And to exchange in between the softwares and in between the different databases, we use, of course, data formats, and I will explain a bit in which direction this is going. Yeah, for softwares, LCA softwares, it's a bit, I would say it's an ancient field. They have been there already, most of them, the last 10, 20 years. They work differently, they have different, like, architecture, software architecture, and very often they're not compatible in how they work and how they look alike performantly. Very often not open source, sometimes also not good maintained, so there's a lot of issues. And good thing, because we talk about ontology, or sometimes some softwares work by name, especially for chemicals. They just go by the name ethanol. Others go by UUIDs, which is a unique identifier, and goes in this direction. So they work really differently, which I just wanted to tell you, because we imagine they all work very similar, but they don't, unfortunately. Databases. I explained today a bit already where they're coming from and what they're representing. Very often where we need databases is something which is general data, like transport data, electricity production, waste treatment. Is something you don't want to model yourself all the time and call your local authority or something. This you rely on databases very often, for instance, like EcoInvent or environmental footprint database, where you get the data from. Can also be in regional context. For instance, we have clients from the US, they use a lot of LCA Commons. We have also clients in Asia, they use HiQLCD, or something like Probus, which is German. Ökoborder is also German. Sometimes the databases have different assumptions, and we need to be a bit careful if we want to mix the data sets. So if you want to do it, we see it very often that people start to mix different databases. This could also go in the direction of cherry picking, where you say the electricity in the one database has a lower impact than in the other one. So you choose the one process, but take it from another one. It's very careful, taken with care, and you need to also think that they have different assumptions, how they work. Also within EcoInvent, for instance, you have different system models, like APOS, cutoff, and so you need to take care that you don't mix data sets, because they have issues. Very often also, what I want to remind, these companies, they're companies or foundations sometimes, they're on the market, they take money for the services. Very often people think that money, like good data is for free, but in this case, it's not. Of course, it's a bit opposite from what the FAIR principles are for. But if you think they're just flying around data, it unfortunately is not. Someone paid for it, or you have to pay it for yourself, just as a reminder. Yeah, I showed this chart already this morning. Just a reminder again, databases can be fully aggregated, like the one on the right, Common Minds, Plastic Europe, Gabi. You have database partly, but it helps also to protect the industries which provided the data sets, but also it doesn't add up to you or you analyzing the situations, the processes. You hide basically the recipes of how things are produced. Hopefully in the future, DF 4.0 database will be transparent and unit process, and EcoInvent is already. So on the left one, it's a bit more transparent, helps also to understand the data, and gives more advice on how things are produced. Yeah, data formats is a really interesting field, as there are different softwares. On the left, you see a lot of different schemes. Also, we have our own schemes. They're very often not compatible to each other. Some are based on Excel formats, some are based on their own formats, and it's not really good. Very often they use XML format, which is a bit more ancient, to be honest, but sometimes also CSV. But you can see, besides LCA, I mean, last 20 years, it was not really harmonized at this logic, but we're a bit lucky because there is the ILCD format, and theoretically you can exchange data with the ILCD format. So the LCA community colleague managed to have one format that you could work with. Doesn't mean it works with all the softwares at the same time, but at least there has been already agreed upon one format you can work with. Yeah, so about FAIR data in LCA, I will mostly find inspiration from the publication quoted here. Of course, findability, accessibility, interoperability, and reusability of data. Let's go findability. I talked about this a bit already, where to find data. So we have search engines, which are done actually from our company, this one as well. There's also now Zenodo, where you can also look up data sets. But elsewise, as I said already this morning, it's not like SciFinder or Reaccess. You can Google it, but you will not find data sets very often. So these are the most prevalent one, but it's very hard sometimes to find data sets. Our company provides a really big platform where most of them are inside, but not all of them. Also, this GLAD network is supposed to help you with it. That you can also sometimes look into scientific publication, and sometimes you have to make the data entry yourself. So it's not really a data exchange format if you need to copy and paste data entries from PDF. Of course, it doesn't help a lot. Talking about accessibility, it's a very interesting topic. We rely very often on background databases. You have a so-called EULA, like an end-user license agreement with a database provider, and very often you're not allowed to share data because you use the database. So if I'm working in a European-funded research project, I produce data and I aggregate the data, so not show anything which is done by the industry partners. We're not supposed to share them. Besides, they also have a license for the background database. So I think it's very problematic that we cannot share data, besides we produce it, and other people cannot take it for them. So it's a bit limiting, the whole situation. Same goes for the EF 3.1 database, which we're only allowed to use within the license, and the license is only if you do PEF studies. So we're not supposed to use it for research, actually. And this is highly limiting what we're doing. So take care. What you can do, you can share always your foreground, because as long as the industry partner allow this, you can share the foreground and someone else can connect it to their background database and work with it themselves. So I think this is something we should keep in mind. I was just made aware of that we need to be very careful about this, because otherwise you will have a legal issue for databases. Yeah, going into the direction interoperability. Softwares, as I mentioned already, work in different fashion. Sometimes we have fully aggregated data sets. We have also mixed modeling approaches and stages, so it's very complicated, and there's a lot of operation freedom because it's a free market. The softwares can do what they want, and so they work at a different logic. If you bring all softwares together, you will see that it doesn't compile with the way they modeled and the way how things are designed in the softwares. What sometimes works good in some softwares, like in ours, for instance, here, talking about FAIR principles, we track in our software, for instance, we have a UUID, which is specific change tracking and version tracking. So it's something which is very often not happening in softwares, but within ours, it's automatically, and helps a bit to track the status of the data sets. Yeah, looking a bit about the factor interoperability, I discussed already, we have a plethora of data sets, and if you work with CIMAPRO or Gabi, it's very likely that you cannot exchange data sets, unfortunately. We need to find a way around very often. The tool we have is one of the most versatile because it can exchange data formats, as shown here on the left. So you can bring it into another form. But very often, what I forgot to say, also the language the softwares speak on naming level or UUID level is not the same. We have different mappings for different databases, and it's very complex. It's also part of our business model because the complexity needs to be done by a consultant to bring things to each other and then work on it. But it's not as easy as some people think. And if you work in one software, it doesn't mean you can just send it to your friend and they open it and it works. You have to do mapping. It's really complicated and time-consuming. Yeah, then finally I want to go a bit into like technical details. So for a long time, the XML format from the ICD format, as you see on the left, as you can see, it looks a bit cryptic or like HTML coding. And something we have developed recently or no, already for a long time is a JSON format, which looks very clean like this. Why is it important? We already heard about AI and machine learning. With this one, it's very hard to run actually machine learning and AI through it. With a clean up JSON format, you will be able to run it through it and also to see very nicely, as you can see, documentation and everything. This is, I think, where the future is going and where IT is already, but the LCA is not there yet. Also, if you compare, because I'm the guy, I think I broke 1 or 2 laptops by implementing a lot of databases, and it took forever, like a day to implement data, because the ICD format with XML takes forever to read and write. And with our approaches, JSON is way faster. Also for really big social databases, it's very important to use this format. Yeah, going to the last step, reusability. Of course, if I do a research project, I want to share the data with you. But as I said, it's a bit limited already to licensing for the things we have in general. Sometimes also the research project asks you to exploit the data sets. going into that we actually sell or market the data sets afterwards. So because it's also a market, some companies' business model is relying on this. And yet we're missing a bit the exchange format. Yeah, and we still missing a bit the traceability. Maybe I get it. Sorry, the modeling approaches are sometimes different softwares, so it's also hard to explain sometimes. This is a topic I wanted to address and is very important in LCA. LCA, compared to other fields, covers very often the data quality. I'm a chemist, if I remember, in the laboratory, I never assigned data quality to what I measure. Also, uncertainty was a bit a topic. But in LCA, we are able to have a look on data quality, where we describe kind of the idea, if we have a process, how reliable is the process, how recent is the process, how geographical is the process, and how recent is the technology. And with this, it helps us a bit to understand the process. So this is a good example from our software, where you can see, we run an example for a computer here. You can see the climate change, this is the result. And most of the data quality is really, really bad. In terms of the time correlation is a 5, so this means it's not really representative to modern days. This helps to understand also, put data into context. So, final words about fair data in LCA. Findability is covered by the data search engines I already showed you. Accessibility is a bit limited by the licenses we have with the commercial license databases we operate with. Interoperability works quite okay, but not perfectly. Everyone has a different mapping, people use different softwares, different data formats, still a problem. And reusability, I hope that in the future we can have more open data in the LCA field, but still we have to rely on the licenses. Yeah, at the end of the day, try to share your data. The unit processes in the foreground are always free, so please try to share the data. That's the point. Thanks a lot.
Thank you, Jonas. And thank you for trying to maintain your voice up. So we can take the questions at the end. So just move to the last presentation of today's session before the pitch session. So I would like to present Angela Serra, that will talk about FAIR principles for knowledge graphs in SSbD.
Okay, thanks for the nice introduction, and it's really nice to still see all of you here after this long day. Okay, so my talk today is about FAIR principle for knowledge graphs. So first of all, I want to ask you a question. How many of you have heard about knowledge graphs before? Yes. How many of you have used knowledge graphs before? How many of you uses Google, Amazon, Netflix? So basically all of you uses knowledge graphs. Okay, so let's go to quick definitions. What is a knowledge graph? So a knowledge graph is a graph that is composed of nodes and edges. Nodes usually represents entities of interest, and the relationships between these entities of interest are the edges. So what is the main, why knowledge graphs are so powerful? Because they can be used to collect together in the same place data that is usually scattered around different sources. But more importantly, we can use these connectivity patterns that we find into this graph to uncover new knowledge, not only on nodes, but also specifically we can uncover new links, so we can find connections that were not there before. How can we do this? Basically, starting from the graph, we can embed this graph in a lower dimensional space, which means that we get a vector representation of the nodes, and you will see there are dots in this embedding space. And based on their distance or similarity in this embedding space, we can predict new associations. So for example, if a chemical is pretty close to a disease, and the chemical and the disease are not connected in the original graph, we can think that this chemical might be causing, for example, the disease. So knowledge graphs are indeed databases, and if I make a parallel with the more classical tabular databases, where we have entities stored in different tables, every type of entities come from a table of a different color, and you see that for each entry of the entity we're going to have, of these tables, we're going to have one node in the graph. So one entity, one node. And then the relationships that exist between the different tables are directly embedded into the edges of the graph. And you see that the graphs have labels on the edges, and these basically tell us what type of relationship exists between the two entities. Of course, in a tabular graph database, we can also store attributes, so more information about the nodes. And here, if you see, for example, in the image on the right, this is an example of a knowledge graph stored in Neo4j. That is just one of the graph database management systems that exist. But all the properties are stored basically both in the edges and in the nodes. So when you click on the node, like on the image on the top, you can see that there are IDs that represents the nodes, but also all the other possible information that you want to store there. This is used to make the node and the information, so the entity, findable. But then you can also store other properties on the edges. So the fact that two proteins, for example, interact, like in this case, we can store information that is, for example, where does this connection come from which database, what type of score has this node and edge, and so on. So what's the advantage of using graphs compared to classical databases is that since these nodes are already all connected, we can basically make queries in a more faster way. We can use all the algorithms that come from the graph theory that already work with linked data rather than joining tables and merging tables and looking for patterns into the tabular format database. Now, let's say that we want to perform chemical safety assessment, and this is one example of a knowledge graph that we have suggested as a possible graph to contain the right information for chemical safety assessment. And this is basically a compound and gene-centered graph, but what we think that the information that should be contained are structural properties of the compound, also possible effects of these compounds, like, for example, is the compound toxic, is the compound associated to some disease or phenotypes, but also we want to study the mechanism of action of these compounds. So what do they do? To which, for example, biological process are they associated with, to which biological system they activate the process into, and so on. So the process that we need to do to build a knowledge graph follows many steps. First thing is that we need to define the objective. What do we want to build the graph for? What type of analysis we want to perform out of this graph? This will lead the second step, that is the data retrieval. What are the data sources that I need to feed the graph with to answer my question? Once we do this, we need to define the graph schema, and the graph schema is basically something that looks like this, that tells you what are the properties of the nodes, what are the properties of the edges, what are the terms I use as properties of the nodes and the edges. And then we need to basically clean and harmonize the data. We need to align this with ontologies. I know that we don't like ontologies, but we need to do that. And then we need to extract and integrate the data into the graph. And then finally, we need to ensure that the integrity of the graph is correct, and then we need to regularly update these graphs. So all of this does not come without challenges, of course. The first challenge is related to the data heterogeneity. Data are really scattered in many different sources. For example, these are only some of the possible sources that we can use to feed the graph that I showed you before. And many of these sources do not come already as associations. So you really need to build these triples of node, head, tail, and relationship. So what is the entity that is connected to which other entity with which relationships? And what's the problem here is that everyone calls the same thing in different ways. Like, these are all terms that we could use to refer to the same gene or to the same disease. But if we go on a database and something is referred with a name, and then we go into another database and it's referred with another name, we end up putting twice the nodes in the graph. So we need to really do an entity recognition task to understand what are we talking about. Do we have already a node for this? Do we have already a relationship for this? Then there's many other challenges that, for example, the schema definition, it's a challenge. Identify what nodes and edges to add that in a way that we are generic enough, but we can accommodate all the possible type of nodes and relationships that we want to choose. The scalability, I mean, these knowledge graphs can really become big. They can have billions of edges, so the computational powers that we need, it's a lot. There are biases, just because there are some entities that are more studied than others. And then there's also issues in the usability, because we need to learn the right query language to use these graphs, so it might not be as user-friendly as we would like to. So we recently have reviewed existing knowledge graphs, because the best thing to do is not to start building your graph, but to see what's available if someone has already built a graph for your purposes. And here I have a list. I don't have time to go through all the possible graphs, but I left here the example of applications that they are used for. Many of them are used as search engines, so you just go there and search if there's information about the entities that you are interested to. Recommendation system, this is basically what Amazon and Netflix do. They would suggest you something similar to what you've already watched or bought. And then these are specifically graphs for precision medicine and drug discovery. So what we realized is that many of these graphs share the same entities. So majority of the data that you find in these graphs are related to chemicals, drugs, diseases, genes. And then there are all the other sources that you see at the bottom are like specific for the graph that you want, for the purpose the graph was built for. So you're gonna find common layer, but then you need to choose which graph has the information that you want. And when it comes to the nodes, majority of the people that have built this graph, they have already aligned these nodes to common ontologies. But when we look at the edges, so how people call the relationship, this is really a mess. There are really like similar words for different things, or 3 different words for the same thing. So if you want to know, for example, if a relationship exists in multiple of these knowledge graphs, you really need to go and double check manually yourself. This I can skip. So when it comes to the fairness, knowledge graphs are always said to make dataset fair, because they are made for connecting datasets, so to make interoperability. But then how fair are the graphs themselves? And then if you want to evaluate this fairness, you need to actually look at all the components. So you need to double check the fairness of the nodes, the fairness of the edges, and more importantly also the fairness of the extracted new knowledge, because the way you use the graph might be different from the way that other people use the graph to extract the knowledge, so you really need to document what you've done when you add new edges to a graph. And now I want to spend the last few minutes of this talk by telling you how we are using knowledge graphs in the InSight project, which is the EU project that we are coordinating at Tampere University. And so far, I've been discussing only about data. But what we want to do here is to build a graph that has 3 different types of layers. We're going to have data that we have them at the bottom. Then we have models and tools. So what are the actual computational tools that you use to analyze the data sets? And then as the 3rd layer, we're going to have the impact outcome pathway. So something that you've seen already in Dario's presentation yesterday, where we want to connect all possible impacts of the 4 impact categories together. So how do we want to use this graph? Basically, people can look at what are the chain of data and models that are needed to address or to predict certain impacts. So we're going to have connections between the data at the data level, but then also connection between the data and the model and the impact categories. And because so far we've been only discussing about connections about data, but models can be connected too. For example, we can have 3 different models that predict the same indicators or the same impact, and we want to build a consensus between these different models. So we have 3 nodes that go into the same node. Or we can build pipelines. So we can have different models. They take data in input, they give data in output, the output is fed in the new model, and so on. So all these things can be represented in a knowledge graph in Neo4j. That is what I have here. I have data set in yellow, models in pink, and indicators in red. And you see that there are data sets that go in input to certain, actually I have also blue nodes that are processed data. And for example, here I have a pipeline that we built starting from the top right yellow node that is omics data. We can go into the node that is called BMDX, and we can perform dose-dependent analysis of omics data. So we can find what are the doses that trigger certain biological reactions. And then this can go into the tool that we call OP fingerprint that can perform OP enrichment analysis. So we can see what are the biological processes that these genes move. And then from there, we can go to another model that we call the integration of omic and PBK analysis, because we can compare the internal concentration that we have with the omics data with the one that are predicted by PBK models. So basically, these tools allow you to query and search what are possible pipelines and possible combinations of data and models. And as future directions of knowledge graph, we have definitely large language models. Why? Because they are already used to parse a lot of text. So we use language models to perform entity recognition and to identify associations between entities. So from text, we use them to build the graphs. But also, there are a lot of new applications of language models for querying and chatting with the graph, in a way, chatting with the graph. For example, there's the Monarch initiative that has built a plugin for ChatGPT, and they have the Monarch knowledge graphs. And you can, if you don't know the query language, you can just go to ChatGPT and chat and extract information with their plugin. But also, whenever we perform a prediction of a new connection, we might want to explain what the prediction means or why do we get this association. And language models are also used there to explain why certain associations are found out. So, as a summary, knowledge graphs are a really powerful tool for fair data representation and not only data. Data must be harmonized before we can inject it into the knowledge graph, and then we really encourage collaborative community-driven knowledge graph development to improve their interoperability. So we really need to have common ground language for the representation of the nodes of the edges. And there's a really growing role of AI in interface with knowledge graphs. So with this, I thank you all for your attention, and I don't know if we want to take questions now or later.
Thank you very much. Okay, so we have time just for one question, and then we should move on. Somebody have questions or curiosities or? No? Okay. One there, okay.
Maybe? Yeah, oh, it works. Thanks for your presentation, it was really interesting. I wondered a little bit, but it's maybe more on the technical side. You mentioned at the beginning that you were using various embeddings for your data mapping, right? Are we out in like PCAs or Perfects, or could you elaborate a little bit on which types of embeddings?
There are really many different types. One that we like to use in our lab is called TransC. That basically applies kind of the law physics, because you have vectors in the embedding space, and you have 2 vectors that represents the nodes, and then you have another vector that represents the relationship. So when you apply a relationship, the vector will move in the direction of the relationship. And this is how you can perform predictions. This is how you can move your nodes toward other nodes by applying the prediction. But then there are shortest path-based algorithms or rotational-based algorithms. There are really many.
So you're using a mix?
We use, basically depends also on the type of edges that we have. If we have labels on the edges, we like to use this trans-E. But if we don't have labels or we have no weights, we like to use the shortest path-based approaches. So it depends on the analysis you need to perform.
Thanks.
Thank you very much again to all the speakers. So if you have other questions, please go directly to Irini and Jonas, because we have to move on. There is this pitch presentation as yesterday, so